So let's start the class now. So today I'm gonna go over some questions in homework 6, and I'm gonna show you extra solution to extra two problems, coding problems. So let's go to handwritten. For problem number 5, which is what is the relationship between PCA and SVD? Since this question is directly from lecture notes, I'm not gonna rewrite the contents that is already in the lecture notes. So the answer to first question is in lecture note 13, page 10 to 11. And second problem is in the page 12, which is how SVD can do a low rank approximation. And for number 3, derive the Fisher discriminant analysis from scratch. This is in lecture note 12 from page 6 to 9. So for problem number 5, you may check this lecture note to find out the answer. For number 8, there's A. Formulate the least square problem in terms of UK, X, and variable W, omega, and this optimization problem should resemble linear regression. So we want to find the weights such that we weight the columns of UK. So we need to find some kind of weight so that we can weight the columns of UK, and we will just minimize the residual error. So thus the objective function can be written as mu UK omega minus X. So this is just basically a reconstruction error because it resembles the linear regression, and we are just giving the weight to the columns of this UK. Okay, so we now have objective function, and since we need to minimize this reconstruction error, we can just write UK omega minus X. So this was answer to problem number 8A. And B, we need to show the solution of the least square problem is equal to UKTX, which is the projection of X on the span of the columns of UK. So before our midterm exam, there was optimization lectures. And in these optimization lectures, we know that answer to this kind of question is equal to, it goes to X, optimal solution is equal to ATA negative 1 ATB. So we cover this in the optimization section, and we're gonna just use this because our basically this equation looks very similar to this, okay? So the minimize of UK, I don't know why. Yep. Omega minus X goes into omega star is equal to UKT UK negative 1 UK transpose X, okay? So here we can look this part, and since we know the property of U is just UKT over UK is just equal to I, okay? So this section is equal to I, so we're gonna just ignore this part, then we can write UKTX. Okay? So basically this, the second part of this problem 8 was just to use the solution that we derived from the optimization section, okay? Any questions to number 8? No? Okay. So next question is problem 11. Problem 11, first part, you use Python to compute the SVD, and now we're going to use our hands to do that, okay? So for problem 11B, we need to solve SVD by our own hand. So we can just find ATA first. ATA is equal to and this is basically equal to 1. Okay. So now we have ATA. We need to find eigenvalues of this ATA matrix. So we can just write determinant of ATA minus lambda I, and lambdas are the eigenvalues. I can say that this is determinant of 1 minus. And if you solve this determinant problem, we can get 1 minus lambda squared, 2 minus lambda. Now we can get this equation, and this equation can be rewritten as 1 minus lambda, and lambda minus 3. So this basically gives 3 eigenvalues. First eigenvalue is 3, second is 1, and third one is 0. And the relationship between the singular value and eigenvalue is quite simple. Singular value is basically square roots of these eigenvalues. So we can say the first singular value is root 3, second singular value is 1, and third singular value is 0. Now we have eigenvalues and our singular values, so we need to find the eigenvector for corresponding eigenvalues. Now, for eigenvalue of first eigenvalue, lambda 1 is equal to 3, we can write the equation negative 2 So this equation should satisfy when we use this lambda 1 is equal to 3. And this will be the eigenvector that we want. And if you just write this equation again, then we can say even though this equation is solved by just setting all x, y, z as 0, but we don't want that, so we can just find right answer, which means that all of x, y, z must not be 0. So the x, y, z that satisfies all 3 of this equation is 1, negative 2, 1. Okay. And we want to change this vector into the unit length, so we will just divide it by the size of this vector, which is root 6. So we can get 1 over root 6. Yeah. So this is the first eigenvector corresponding to this first eigenvalue. Now for second eigenvalue, which is 1, we can just write the equation this gives us minus y minus x plus y plus minus z. So this equation gives us y is equal to 0. But for the x and z, there should be different sign. X and z should have different sign. So we can just write x, y, z is equal to 1, 0, negative 1. Okay. And also we want this vector, eigenvector, to be a union length. So we can just divide this vector into the size of its vector, which is root 2. And we can get the second eigenvector as this, okay? Now, we want to find our third eigenvector for lambda 3 is equal to 0. So this matrix can be written as so we want to find x, y, z that satisfies all of these three equations. And if you set x is equal to 1, then y will be automatically become 1. And then z will become also 1. Okay? So we can just find out x, y, z is equal to 1, 1, 1. Now again, we need to change this vector into the union length. So we're going to just divide by root 3 to make it union length. So V3 will be root. Okay. So now we got all three eigenvectors, V1, V2, and V3. And we're going to use these three eigenvectors and the singular values and eigenvalues that we computed in order to find the SVD. So in order to make A is equal to U VT, we need to find this U, okay? And this U matrix can be easily found by using this formulation. U1 for the first column of the U vector can be written as AV1, okay? And we know the first singular value is 1 over root 3, and A is basically given in the problem. And V1, we computed V1 here. And if we compute this matrix, this gives us now using the same methodology, U2 can be 1 over sigma 2 and AV2. And sigma 2 is just 1, so you're going to just ignore this part and the V2 here is written as there. So V2 and we can write this as like this. So now we got U1 and U2. And what about U3? Since this third singular value becomes 0, we can now just compute U3. So we only have U1 and U2. So now using this equation here, we computed U, okay? U columns of U. Just write it down here, okay? And we find the singular values. Although the third singular value is 0, we have first singular value as root 3 and second singular value as 1. So I'm gonna just write here roots 3, 0, 0, 1, 0. However, the third row is just disappeared because our third singular value is basically 0. So we're going to just write it like this. And here, which is Vt, and V is just eigenvectors as we computed here, V1, V2, and V3. So V1, V2, V3, and transpose. So this is basically the singular value decomposition of this A. Okay. So in problem 11C, we need to compute the rank 1 approximation of this matrix. Okay. So rank 1 matrix, we can just write sigma 1 U1 V1T, which means the sigma 1 is root 3 here, root 3 times, and U1 we computed here, here, okay, U1, and V1T is, we computed V1 right there, so transpose of that matrix, of that vector, is equal to this. Okay. And if we compute these all three, we can get this. Okay. So this is basically the rank 1 approximation of the matrix A. Okay. So any questions regarding this kind of singular value decomposition and row rank approximation? So I think in this PCA and SVD chapter, problem 11 is quite important to solve because you need to know how to compute SVD rather than just using the simple code embedded in the Python. Okay, I think it's very important to solve this kind of question by your own hands.
네. A 트랜스포즈 A로
네.
그냥 A 트랜스포즈로 구하는 거는 그렇게 구하면 그 V가
네.
저렇게 3x 3이 아니라 3x 2로 나오는데 그렇게 구하면 안 되나요?
AAT라고 하고 이제 구하면 안 되냐는 말씀.
네네네.
AAT. 제가 그거 한번 생각을 해보고 말씀드릴 수 있도록 하겠습니다. So if you guys don't have any question, then we're gonna just move the coding problem. So this is problem 1 in our coding problem. So first is to plot the uniform distribution and normal distribution of 100,000 data points. This is quite simple. We can just reuse the rand function embedded in NumPy and the rand_n function embedded in NumPy. So you're going to just create 100,000 data points. Yep. Okay. and this is the result. So this is quite simple, so I'm not going to just explain this kind of thing. And second part is we need to select 100 data points for 10,000 times for each distribution and show the mean of the sample data points goes to a normal distribution. Okay. So first we use for 10,000 times. We're going to repeat it for 10,000 times, and we select 100 indexes from the data we just created above. So in this uniform and normal, we just created the random numbers, and we're going to just choose index of these 100 data points and then use this data from the index chosen randomly, and we're going to just use the mean to append x. So we're going to just create this S matrix by giving the mean value of this data, and this data can be achieved by selecting 100 random numbers of index and using this index to make the data. Okay, so this is basically simple problem, so I'm not gonna just go over it. And this same, just change it to normal here rather than the uniform. This algorithm is all same, and we can see that the mean of the distribution goes to normal distribution, and this is, that's basically what we wanted to look at. And now we are given a new data and this data here, and we want to find the covariance matrix and use correlation coefficients. Okay. Now covariance matrix can be computed simply by using the NumPy curve of a data. Data is just the data here we just get. Okay. And in order to find the correlation coefficient, you're gonna just use the definition of correlation coefficient, which is that, given us like that. So just use that function to find the correlation coefficient, and we get this kind of answer. So this problem 1 is basically a simple problem. So I'm not sure why this problem is in this dimension reduction area, but okay. I think the problem 1 is quite not important in our class. So let's go to problem 6. Solve the problem with Fisher discriminant analysis and plot the projection line. So our data is given like this, and we want to do the FDA on this data and find the projection line. Okay. And here, so if you remember this FDA part, FDA can be written as like now here the mu0 is the mean of this data that corresponds to label 0, which in here we have two kind of data, x0 and x1. Okay, so this mu0 is just basically the mean of this x0, and mu1 should be the mean value of this x1 data points. Okay, and S0 is basically the sample variance of x over 0, and S1 is sample variance of the data that corresponds to x1. And S0, which can be written as like this. Like this, okay? So we can just rewrite it in our coding, and S1 can be just rewritten by changing this x0 to x1. Now, FDA can be used in the situation where we have clear labels for the classes. So we can just write x0 and x1 like this, okay? So we're gonna find this W by computing this kind of equation. Now I guess this A term is just ignored here. After finding this W, we can just calculate the slope with h, which means the y is equal to h over x, and this is basically the slope of the line. So this xp, you don't need to know, but xp is just setting the data points in the x-axis, and we're going to find corresponding data points for y-axis so that we can just draw this kind of line. Okay. So now you see the answer be like this. Okay. This is FDA projection line. So FDA consider the level of each data points. So we can just first group these two classes and use separately for the FDA analysis by using this kind of equation. Okay. Now the second part goes into the PCA, and PCA is quite different from FDA. So FDA, we can use the labels clearly mentioned in our data. However, in PCA, we cannot consider this kind of label. So we're gonna just merge these two classes into one by using the V-stack, vertical stack. So vertical stacks, using the vertical stacks, we created new data X, which is basically the X0s over here and X1s over here. Okay. So since PCA cannot consider the label of each data, we just merged two classes into one. And here, S can be written as like this, but as you remember, the PCA is maximizing the UTSU, and S here was XTX. Okay. So we find this X matrix here, and using this kind of function, this is basically eigenvalue decomposition or eigenanalysis on the matrix X, S. So we find eigenvectors and eigenvalues, and I know that D is eigenvalues and V are eigenvectors. So with this AuxSort, which is basically sorting the eigenvalues in order of the big sizes, so by using this kind of AuxSort of minus D, you're just changing the index so that the biggest eigenvalues come first rather than the smaller eigenvalues. So we can just change our eigenvectors in corresponding order of the eigenvalues. Okay. So with this, rest of thing is very similar. We find the slope by using the eigenvectors we computed before, and we generate the x-axis data points, and using this kind of slope, we can just find the line of the PCA. So now the projection of the PCA line is quite different from FDA. So PCA and FDA considers a level of each data class, but PCA doesn't, and PCA just need to maximize the variance. So now our result looks very good. Okay. Any questions regarding problem 6? I think this is quite simple because I know in lecture note this PCA code was given, and also this FDA code was given in the lecture note. So you just can use the code in the lecture note. So this question is quite simple. And also, in my knowledge, the PCA and FDA is defined in some kind of library in other sources. So if you don't want to just compute PCA by this mathematical formula, you can just use the function already written in Python packages like NumPy or other things, or scikit-learn or other things. Okay. So this is basically the mathematical way to find the PCA. So and FDA. 네. 네. 아, 제가 알기로는 원래 노멀라이제이션을 해야 됩니다. 근데 제가 알기로는 이게 아마 이 데이터를 만들 때 자체에서 제가 이 데이터 포인트를 만들 때 아마 평균을 0으로 해놨긴 할 겁니다. 아, 그런가요? 아, 맞네요. 빼줄 텐데. 원래 제가 알기로 그 X 데이터가 있으면 X 데이터에다가 평균을 빼고 진행하는 걸로 알고 있는데, 네, 이거는 이것도 다시 한번 확인해보고 말씀드릴 수 있도록 하겠습니다.
빼고 한 거랑 빼고 하는 거랑
네, 조금밖에 차이 안 난가요? 네, 알겠습니다. So for the problem, next problem is problem 10, but I'm not gonna go over the problem 10. I'm gonna just upload the solution to problem 10 in PLMS, so you can just check that out, okay? So for problem 11, so we computed the SVD with our hand in the handwritten section, and now we're gonna just compute SVD of this matrix A. And this is quite simple because SVD is already defined in this NumPy package, so we can just write matrix A like that and use SVD function to find U matrix, the singular values, and eigenvectors. Okay. And after we get this U and S and VT, you can just change this U as a matrix by using the A as matrix function over here. And also for S, we're gonna just use the diagonal section of the X, which means the singular values of the X. I'm not sure why we're doing this because I think this X matrix is already a diagonal matrix, but okay, so we're gonna just use diagonal of this X matrix so that we can find the singular values. Okay, and the answer is like this. And also, this kind of code is also given in the lecture notes, so I'm not gonna. I don't think this problem is hard for you guys. So just use the SVD function defined in NumPy. So this is problem 11. Okay. And for problem 13. So we have, in the lecture note, we have demonstrated the PCA algorithm with spring and mass system. And our result of this PCA was this. So this image is retrieved by just multiplying the principal component into the data X. So we're gonna just do the same thing. We're gonna just find these singular values with SVD, and gonna just multiply these singular values in the original data X so that we can find this kind of equation, this kind of waves. So basically the first principal component of this data has a big magnitude of the data, which means the PCA principal component 1 contains biggest data compared to other principal components. So we're gonna just do basically do this kind of thing. So as you know, in problem number 5, which means what is the relationship between PCA and SVD, when you guys solve this kind of homework problem, you may notice that PCA and SVD is like very related to each other. So this is just opening the data. I'm not going to cover this. Okay. And this is drawing the data. So like someone mentioned before, you have to normalize the data by subtracting the mean of X to entire data. And this normalization process was not done in above questions, so I'm going to just go and find out why it has not been done and tell you guys why. And this finding the U matrix and singular values and eigenvectors was done in the previous question, so I'm not going to go over this. And the same, okay. Now, if you print out these singular values, the singular values, you can find out the relative magnitude of the singular values here. As you can see, because singular value is very similar to the eigenvalues, which is lambda is basically equal to over squared. Okay, so first singular value has biggest magnitude, and the second, third and 4, 5, 6 then have singular value of below size of 500. So basically the first singular values contains the most of the information. So if we multiply these singular values into our original data in order to find the relative magnitude of each singular values, we can just find out this kind of answer, which is very similar to PCA. So one may ask, hey, why are we multiplying these singular values into our original data? Basically, this does not have any physical meaning, just we want to find the relative magnitude of the singular value. So this kind of graph just tells us everything. So the first singular value, which is low rank 1, just contain all the data we wanted. And 2, 3, 4, 5, 6 are basically the supplementary. So when we do the dimensional reduction, so we want to reduce the dimension, but we want to maintain our data as many as possible, which means we don't want to damage the data by the dimensionality reduction, right? So when we do the dimensionality reduction, we will use this first singular value to do that, because first singular value basically contains the whole data. So dimensional reduction is basically reducing the dimension without damaging the original data. And in order to prevent damaging the data, and we want to maintain the original data as many as possible, so we can just use the eigenvalues or singular values to find out which singular values we contains the data. So if second singular value has the large number, like 1,000, then maybe considering the low ranking 2 for the dimensional reduction would be better than just using the first singular values. Okay. So now we have covered all problem except solution problem number 10. I'm gonna just upload this problem 10 in the PLMS so that we can go over some new questions that were not given in the homework. So for the first problem, I'm going to go over is problem number 3. And this is also basically simple problem, I think. So we have two kind of data, X and Y. And we will do the regression analysis first in order to find the relationship between X and Y. So in the linear regression, we covered this using the CVX-Pi before our midterm exam. So I'm not going to explain details about this. So this kind of coding should be very familiar to you because you have studied for the midterm exam. So this is basically the linear regression between the X and Y. And if we find the linear regression line between X and Y, you can just write this kind of line, okay? And the second, we need to perform the PCA, and here again, so we need to normalize, but the mean of X and Y is already 0, so we're gonna skip the normalization step. So PCA does not consider which level. So as we did before, there was X0 and X1. But in order to do the PCA, we just merged this X0 and X1 into one. So instead of VStack, VStack is basically the vertical stack, because we know this all of data is corresponding to X. Okay. We are going to use the H stack, which is horizontal stack. So X will be here and Y will be here. And if we merge the data into one, and we can just use the AIDS matrix in order to change this data as a NumPy matrix. And this is basically the same thing that we had done before. So finding the eigenvalues and eigenvectors and sorting in the size of the biggest eigen values and vectors. And if we draw the line of this PCA, we can just find out that it is very similar to the linear regression line. So in PCA, So linear regression and PCA is almost same in this case. So I think the PCA is trying to maximize the variance and minimize the reconstruction error. So minimizing the reconstruction error part is very similar to linear regression, and we have covered this in the handwritten problem number 8. So I think the PCA, first principle component, and PCA and regression analysis is basically giving the similar result over there. So in this problem, this PCA code is very simple, and above linear regression, you just covered it before the midterm exam. So I don't think this problem number 3 should be any difficult for you guys. So any questions about this extra problem? Okay. Second extra problem they want to show you guys is problem 12. Problem 12 in here, so this situation is quite difficult to understand, I think. So we have one video, and in our video, there are a total of 20 frames, okay? Which means the video is composed of 20 images. Okay? So by merging these 20 images, you created a short video. So if you plot the first image, you can see that it looks like this, okay? So this is the first frame of our video. And the next frame will be like maybe this person moves to here, like this person moves to here. So this video is just stacking these kind of image frames, okay? So now there's a specific instruction in order to make the data. So first, you're going to load all the 20 images, and we're going to just merge it into a single matrix. So we need to load the image into grayscale, okay, and reshape each picture as like this, okay? And then we're going to stack them to form matrix A with the shape of row times column times 20. So basically, we want to just load the image. Maybe the image was not grayscale, maybe color scale, which means that if our image was originally the color image, then we're going to have RGB value. So the data might look like this. However, since it says that we need to consider only the grayscale, and we need to reshape the pictures like that, we're going to use color converter so that we can use this color image into the grayscale image. If you do that, we can just make this image in this kind of form. After we do that, we need to stack these images in order to form matrix A. So this I is equal to 0 basically means for the first image of the 20 images, we're going to just define new array, which is flat vector, and which this is basically simple. The image shape will be the original shape, which is image shape here. Will be just row times column times 1, row times columns, okay? And array, you just every pixel values of the image, and flat array is just reshaping the. So basically, this was our original size, right? But we want to change this R times C, and then stack these 20 images, right? So this is basically this first part is just changing this R times C times 1 into R times C. And then we need to stack this R times C 20 times in order to create R times C times 20. So this is quite simple, and you just, after the first iteration, first image, we're gonna just stack the second image into the matrix that we just formed before. So basically, the R times C of R times C matrix is given like this. And we're gonna just stack R times C and stack, so that we can create this kind of tensor, I guess, 3D matrix, okay. So now that we have A matrix, we're going to use the singular value decomposition of this matrix A and plot singular values. And this step is very simple, so I'm not going to just cover it. And if we just show the singular values, then we can see the first singular value is the most important singular value compared to others, because the first singular value is just everything contained in this, containing the whole images, whole data. So if you use the low rank approximation of matrix A with k is equal to 1, basically we're going to just consider the first singular values only. Then we can write equation like this, okay? So A hat. So this is called also truncated SVD. I'm not sure if Professor Lee has mentioned this before. So truncated SVD is basically A dash is equal to UT. T means truncated, and T. So in this truncation, we're going to use this kind of first column of U and the first value of a singular value and the first row of this eigenvector matrix. So we're going to just use the first column here, and we're going to use the first singular value, like S 0, 0, and VT, we're going to just use the first row of our VT matrix. So using this knowledge, we can just print out our first row rank approximation, first rank approximation. So now you can see that all the people which was moving or disappeared, and our background is just maintained. So this basically means that singular values composed all important information in our data, and find that our background is important. And because the people is moving, so maybe the singular value decomposition thought that these kind of moving persons are just outliers or wrong data and just removed. And first singular values contains the most important information in our data. So our most important information in our data was our background, because our background didn't change for entire 20 frames of images. So now, so all the persons are disappeared and our background is remained. So why we have the above result, you can just read it out. So decomposition of A into U, S, and V by applying the SVD method, we can reconstruct A by row rank approximation, because the background is almost same for each frame, and the information will be contained in that. Okay. So basically, in all data, the background was contained every single times. So the background was very important for in this kind of case. So this problem, number 12, is quite interesting problem. Just deleting the humans out of our video frames. So any questions regarding this question? Okay. No? Okay. So basically, we're using the singular value decomposition, which code is not very hard for you guys. And we're just using the row rank approximation by using this kind of equation. And we use the k equals 1, which is the first rank. And we can just use the first column of this U matrix and first value of singular value and first row of the VT. If you guys don't have any question, I'm going to just end the class right now. Okay? Thank you.